Maurizio, we are here to talk about today about the difference between the fundamental difference between traditional cooling and the thermal management approach that Gemateg has to offer. There is a lot to talk about it, but I wanted to chat with you today so that you can give us a simple explanation about the difference. And this conversation was started. I think we were talking on Wednesday about an announcement. And the company is Corinthis. They released now a new technology that is called microfluidics. And that's how we started talking about, this topic at Gemateg. So I'd like to explore that question with you. Are we sure that the traditional cold plate uh, approach is the right way to go in the industry? That's kind of the overarching question, right? So that's how we started.
Sure.
So,
Yeah.
go ahead.
So the
All right.
industry has
Yeah.
been caught off guard because up until a few years ago, and even today, majority of the data centers are air cooled.
Mhm.
Clearly, there's a threshold, and the new technology, the new chip, the new directions that especially AI is prompting forces to go away from traditional air cooling. And so we're entering into the liquid cooling. Liquid cooling is not new. It's been
Okay.
on for quite some time. And the way the overall arching mechanism works is very simple. It's very similar to what you have under the hood of your car. You have a fluid that
Mhm.
goes inside of an exchanger, heat exchangers, and the heat exchanger is on top of the area that you want to cool. And all
Mhm.
of a sudden, you have the heat that is extracted. So this is definitely more efficient than air,
Mhm.
and it's definitely the way to go because especially with AI workload, you won't be able to do it with air.
So,
Now,
so, so it's like a big radiator on top of the chip. That's the
correct.
analogy with the car. Okay.
Exactly. So the major difference is this radiator is getting smaller and smaller, and there are a lot of technology, including microfluidics or dual phase cooling, that are making this exchanger extremely efficient. The way it works is, let's take an example with microfluidics. Conventional cooling solution, liquid cooling solution with the cold plate, they all have parallel channels.
Mhm.
And so in other words, imagine it's very similar to the example, it's an R-way. So if you're an R-way, you have lanes and all, imagine and these lanes are for whatever reason separated by walls. So
Mhm.
instead of having car, you have fluid. Fluid goes through the lanes, and basically by contact with the hot part, they're able to extract the heat. The liquid is cooler,
Mhm.
the walls are hotter, and all of a sudden you have extraction of the heat. That's the principle of the way it works. Then you can get more sophisticated, and instead of using conventional fluid, you can use two-phase fluid. Two-phase fluid is a very efficient. What it means is basically it evaporates at very low temperature.
Mhm.
So, and everybody knows that evaporation is a very probably the most efficient way to extract the heat.
Mhm.
And you still have your lanes, but at this point you are able to maintain the temperature constant and extract the heat efficiently.
So you said,
Uh,
I'm sorry to interrupt here, but
Go
you said
ahead.
two-phase cooling. Is that right? Is that the term?
That
Two-phase
is
cooling?
correct. That is
Okay.
correct. What is
And
happening is it's a fluid that evaporates
uh-huh.
at a lower temperature.
Okay.
When you're French, but I'm sure you cook pasta, and when you cook pasta, you basically put water inside of a pan, and this is boiling at where we are around 100 degrees Celsius. So
Mhm.
imagine, and when the mechanism is fascinating because when you're boiling, the temperature stay constant, but you have a very efficient way to extract the heat.
Hmm.
And that's probably the best and the most efficient way you can think about it. And imagine that you have a fluid that instead of boiling at 100 degree, boils way lower. So
Okay.
at this point, you don't need to have the chip reaching 100 degree, which is going to be frying the chip, and you are efficiently exchanged. That's one way to do it.
Right.
Another way to do it, which is not as new, is called microfluidic. I'm gonna show you a slide
Yes.
of the latest announcement that could
That'd
be
be great. Yes. Yes.
that could be helpful. And so basically, Microsoft has announced that they are exploring,
Mm-hmm.
not implementing,
Hmm.
implementing this technology.
Hmm.
That's a cold plate that is on top of the chip. But as you can see here, instead
What
of
we
having
Yeah. What we see
this,
here is the face of the quote unquote radiator you were explaining earlier.
that is correct. So what you're seeing here is instead of having the regular channels that you normally, as I was mentioning before, the lanes in the airways, what you're seeing here, you have a way more complex pattern
Uh-huh.
that has some similarity, for instance, on the capillaries on your body. The
Okay.
beauty of this system is it has a very sophisticated way of extracting the heat because based on the density of those channels, more channel you have, more dense are the channel, more
Hmm.
fluid you have,
Hmm.
and of course more heat you are able to extract.
Mm.
Uh, so the beauty of this technology is definitely you are able to address what is called hotspot. You
Mhm.
have areas where you have hotter chip, so you can put more water on it, more fluid on it. You have area that are less dense, and then you address it accordingly. Now, this system has some drawback, of course, like any other solution that you have in the market. First of all, these channels are very small. That's the reason why they're called micro channels, which means that instead of having the size of the lane on the airways is basically in the order of air, so less than 50 microns. Microns.
Compared to a
Mm.
lane, what's the how small is that compared?
Usually you get to 200, 300 microns. I mean, you have the technology they're using right now is probably this, you can go 10, 20 times smaller than that.
Okay. Okay.
Uh, and of course, smaller means you can put more. More you means that you can have more surface that you can actually cover with water. The problem is,
Hmm.
number one, you need to push the water through all these channels. The more channels and the more energy you need
Hmm.
to spend to do this. But
Mm.
then this solution or any other solution fundamentally is affected by the same identical issue. You are relying on the temperature of the fluid that comes from the data centers. Let me explain it to you in more clear terms. No matter how good you are with this capillary approach
Hmm.
to go everywhere in your chip, you're still relying on the baseline temperature that is provided by the data centers.
Hmm.
That's a fundamental concept, which means that more power the chip will produce, and more you have to lower this temperature. You may have a better uniformity with the solution, or
Hmm.
you have a better heat transfer with dual phase than conventional cold plate. Of course, spending a little bit more in terms of complexity and cost of the entire system, but you're going to be bound by the temperature of the fluid. It's very interesting because despite the fact that temperature and heat transfer are, of course, correlated, you never hear from cold plate manufacturing any discussion on where and what is the temperature at which the chip are operating. You always hear about how much heat flux they're able to extract from the system. And that's the fundamental difference between active thermal management and conventional passive thermal management, because uh, we believe that those solutions will force data center to spend a lot of money in cooling the water when the chip are going to be more powerful. And this is not going to happen 10 years from now. Let me show you something that I believe it's important that you see.
Before well while you set up the the visual here, I just want to recap because there's a lot there's a lot of aspects here. I just want to recap the challenges and limitations that we see in traditional cold plates, whether it's microfluids or not. Because my understanding is that they basically fall in the same category. Is microfluids is an incremental improvement, but fundamentally it's based on the same approach of traditional cold. So the challenges that I heard are the last one you mentioned is dependence to fluid temperature intake. Is that the right term? Okay. All right. Then the uniformity of the thermal exchange. And then the limitation in terms of the size of, lanes are bigger, microfluidics, sorry, are thinner, but fundamentally limitation in terms of the flow. Did I get that right?
Yeah, and again, the fundamental issue is the main drawbacks is you are bound by the temperature that the data center is providing.
Provides.
That's instead of, I mean, we can get as complicated as you want it, but
Yeah,
fundamentally is
that's it.
imagine that you are operating your data centers in the middle of the desert or summertime in Europe.
Uh-huh.
The temperature outside is 40 degrees Celsius, and all of
Mhm.
a sudden you have to cool it down this chip, and the water, so the fluid that you need to get has to be such that you don't fry in the chip. The
Mm.
higher is the power, the more you need to go down. And so you need to activate chillers, you need to have an extremely complex infrastructure in order to guarantee that. So
Okay.
the problem is
So,
every solution that has been presented so far is at the end of the story a permutation of the fundamental concept of a cold plate,
mm,
of a passive heat exchanger. And
mhm,
now the problem is, so far, so good. But the problem that we should have learned when in 2023 ChatGPT came out and caught everybody off guard is
mhm,
fundamentally this one here. You have two major concern right now. Concern number one, in the next 3 4 years, you're gonna see an incredible amount of power coming out of small compact chip, the
mhm,
size of this board.
mm,
This thing here is gonna produce in 3 4 years 3 4 kilowatts, which is the power that you have on the oven on your house. That's a number one issue. The higher is the power,
mhm,
the lower has to be the temperature from the inlet, which means that you actually, with this solution, you actually transfer your problem outside.
okay.
Transferring your problem outside of the data centers means that you have to have an infrastructure that is extremely expensive because you have to cool everything the same way everywhere at the lowest possible denominator. That's the
Okay.
number one challenge. The second challenge that is as powerful as the first one is chip of new generation. And this is an example. This is the NVIDIA, uh, sorry, GB200, which is the latest and greatest in the family, as different regions that are operating in different conditions. For instance, on the AI, you have two main workload. You have training and you have inference. Training is done constantly on the background and is basically collecting all the data and coming up with a model. Inference is when you ask ChatGPT a question.
Mhm, mhm,
Now, inference is heavy on memories.
mm.
Learning is heavy, training is heavy on computation. And these chiplet are divided into area. Computation, that is the central one, and memories on the side.
Could
So
you
if
zoom a
you,
little bit? Could you just zoom a little bit maybe so that we can see where exactly on the diagram there? Thank you. Uh,
okay, sorry, sorry, let me do this.
Perfect. Thank you. That's great.
So you have memories
Uh-huh.
and other stuff. And then you have the actual computing die, the GPU per se.
Okay.
Everything is in a package is a GPU, but this is the portion of the die that does the computation.
Okay. Okay.
So the problem is, in order to have your machine, your prompt respond quickly, you need to have a lot of memories right next to the chip, and those memories are complicated, and they are becoming more and more sophisticated.
Mm,
Problem is, you don't have homogeneous chips
mhm,
in a chip. You don't have homogeneous chiplet. You have region that have different type of parameters or tolerance to temperature.
mm,
If you go with microfluidics as well as, and even worse with other solution, you may make this a little bit more dense in the area that you need to cool it, but you cannot change it. So in other words, in the workload shifting, sometimes you have this area that is hotter than this,
Okay.
and sometimes not.
Okay.
So you cannot switch the pattern of your capillaries
Mhm.
from one area to the other. That's
Mm.
one problem. But even worse than that, with the power increasing, you will have to go down with temperature
Yeah.
of the fluid coming from the primary, which means extremely cumbersome and expensive chiller outside of your data centers.
So, and so that's beautiful because that's where I think the car analogy that we were talking about earlier stops. Because in a car, um, the engine, I mean, for the given car, unless we change the engine, is always pretty much the same temperature unless you drive really, really, aggressively everywhere, right? Whereas here, that's why I said the analogy stops. Here, what you're telling me is that based on what the chip is doing, what you ask the server to do the operation, either whether inference or learning, those hotspots may move. So it's interesting that the design of the microfluidics is determined ahead of time when we know that the hotspots are going to be different every time. So that's fascinating to me. How is that possible? How do we make that guess? I don't know.
So no, it's again, everything is forced by the way AI is working, but
Mhm.
also, I mean, other applications are similar in behavior.
Okay.
The problem is driven mainly by packaging. You're trying to package in as much as possible, in a more dense envelope, as
Mhm.
much as possible. So, and that's why you come up with this type of architectures. And now these architectures are at this point so that were originally spread out in different areas, so you can fire them up on and off depending on the workload. Now they are all compact, so you have a lot of power, all concentrated, switching from one place to another. That's the worst of the nightmare possible.
And it's going to get
That
worse.
yeah, I mean you can see here. I mean we're
They're
talking
going to get,
about.
yeah, more powerful and more complex over time in the
So
coming
if
years.
you want to understand the difference, the fundamental difference you have on this scheme here. So here you have a conventional cold plate, and it could be as sophisticated as you want. It could be single phase, dual phase, microfluidics, and you can have I don't know, micro channels. You name it.
Uh-huh.
But fundamentally, you are cooling everything the same way at the same
Everywhere.
time.
Okay.
So, and that's gonna force you to, as the power of the system goes up, is going to force you to go to lower and lower temperature.
So that's when you say we're pushing the problem outside the
Exactly. So our system is you leave the outside happily in whatever comfort zone that they have and it costs less. But then
Mhm.
you have something that is similar. You can see this micron here is not by chance because actually Gemateg it has a little bit of an exchangers that is done with microchannels, but not capillary like the ones that you're describing. More conventional in a sense, but more also extreme on others because it's not parallel lanes. But
Mm.
underneath, you have a layers that is a smart one that is actually active. And what it does, it being a micro heat pump, you can regulate this so that it can extract heat in different regions based on the actual workload. So you have a shift from something that is passive, you're relying on the external water
Mhm.
fluid to cool it down, to something that is active, that is turning it on and off depending in a surgical way on the actual condition. And you can imagine that this simple approach is a completely new paradigm shift because the concept of heat extraction changes completely. It's not conventional, it's completely new. It's almost like you have created many, many tiny, super efficient micro chiller that are attached to the chip. And therefore, you shift the problem from relying on the outside to getting inside, but extremely more efficient, where you can actually control it and make it more effective.
Very clear. Very clear. Okay, the difference is very clear now. Um, let's go. They're perfect. Let's go back over to you because this conversation now is taking me to I get the fundamental difference between the Gematec technology and the traditional, even with microfluidics. Um, but I know that at Gematec we have more than the what you showed us is called the product. I guess is called DATEC, right? That's the DATEC part. But there are Gematec is an ecosystem. There are more. There's more than that. So can you walk us through what else is there? I know that when we have multiple of those Gematec system in one server, or even many in a data center, you have to do so. You have to orchestrate them. So can you walk us through this and what happens at that level?
Okay, the thermal management, that is an overused statement because everybody say that it's doing thermal management, but actually what we mean by thermal management is active thermal management is a paradigm shift. What I
Okay.
mean by that is the moment that you have an intelligence locally positioned on the chip that you
Mm,
can turn on and off, at this point, it gives you a great opportunity of creating an intelligence that control this portion of your cooling machine. So
mhm,
now you have a cooling machine that you can actually modulate and regulate.
mm,
So at this point, the moment that you have this ability opens up opportunity that were unthinkable on any other consideration and makes it extremely modular and efficient for data centers. Let me explain you why. So imagine that you have at this point the equivalent of a cold plate, a smart cold plate that is our, which I don't like to call it that way. So I'm not sure if you can see it.
yeah, I can see it. Yes. Yeah.
So right now you have
You can go in
every,
present. You can go in presentation mode if you want, Maurizio. Yeah, this is good. This is very good. Yeah.
so right now you have every chip in your data center as a DATEG
Hmm.
that has the same form factor of a cold plate, conventional cold plate, but is a smart cold plate because it's an active machine, cooling machine. It's almost like compacting a refrigerator inside of multiple refrigerators, actually, inside of a chip.
Hmm.
Now you have an intelligence that has the ability to control each one of these
Hmm.
in a way that is that you decide, because I don't believe it that all the data centers use all the machine 100% of the time. Even when you see workload utilization 80%, doesn't mean that 80% of the machines are working 100% of the utilization.
Hmm.
Therefore, you have chiplets that are super utilized, others that are not utilized. With any other solution that you're having right now, microfluidic, dual phase, cold plate, you are cooling everything the same way. And when you're starting to have thousands of chiplet, this is extremely expensive
Right.
because
Yeah.
so now you have a system, you have a way where you can turn it on and off, or actually modulate it. More some, more other, less others. You
Hmm.
can make sure that thanks to this brain, you have the ability, number one, to control in a very smart way, in real time,
Hmm.
every single chip, so the data center is actually operating. So again, when I'm talking about a paradigm shift with this technology, it means that you have, for the first time in the history of data centers, the ability to actually control 40% of the power consumption of a data centers. And you can control it as complicated as you want it.
So I see here on that slide that you can do if that's if I follow your reason. Could you put that slide back, please,
Of
Maurice,
course.
down the because there are some interesting points on the right where I want to get to the specifics when you say it opens to incredible possibilities first time in the history of data center. What are we talking? I read here data collection optimization, localized cooling. We just talked about that, but then I see things like now we can do maintenance and we can integrate monitoring better, and we can also what can we do with AI, for instance. I see that it's on that slide.
So again, we have pilot installation at our customers, and what we are learning is that every customer has its own specific needs, its own specific workloads, and so on. So the AI-driven thermal management means that instead of having one solution fit them all, you have a customized, personalized solution that actually learn from itself and adjust from itself and optimize from the data that is coming from the data center. So depending on how the workload is spread out across the data centers, you have the ability to control which chip in which row, in which server you can cool it more than others, and that dynamically. And
Yeah.
since you may have situation where you have repetitive workloads, all of a sudden you have a maximum optimization of your resources. So you can do with the same type of energy way more,
Mhm.
or with more energy, with the same energy. I mean, or saving energy if you don't
Yeah,
need to do
less
more.
energy. Yeah, yeah.
Now,
So
predictive maintenance is super crucial because the question of predictive maintenance means that you have the ability to plan. Imagine again a data centers where you have thousands of chiplets everywhere spread out. If some of them are not working properly or fine, are not performing as expected, now you have tools that is telling you, hey, listen, based on historical data, this chip you need to take care of this. And
mhm.
therefore, instead of doing troubleshooting that requires a tremendous amount of resources, you can go surgically to the specific area, to the specific node to intervene,
Mm.
minimizing the downturn. So the idea is that Gemateg has is not necessarily to solve the problem of overheating the chip, but is actually using overheating of the chip as an opportunity to create a new universe in terms of a new paradigm, in terms of how you manage a data center.
Okay, but wait a minute. You said not managing the problem overheating. I thought the point is to maybe also avoid overheating and damage and things like that. So does the Gematec solution also takes care of that?
Totally.
Okay.
So,
Okay.
but again, it's not our end goal. I mean, we believe based on the data that we have on the field that we not only address this issue now, but we are future-proofing the data centers. What I mean by that is we have a modular solution that fits them all. While microfluidics versus dual phase versus cold plate
Uh-huh.
requires major engineering anytime you go from one family to another, and you may get to the point where at certain point those solution won't do the trick because you will need to have waters that is extremely cold. Our solution is modular, so it's thought to address the problem for the next 5 generation of families, but
So
that's not.
yeah, so no, sorry to interrupt because I just had a aha moment here because that implies that in the traditional model, every time we change chip generation, we have to install a new kind of cold plate, a new microfluidics design, for instance. Is that right?
I don't want to get too technical, but
Okay.
there's a parameter that is extremely important, and it's called thermal resistance.
Mhm.
Thermal resistance gives you a somehow an understanding of the efficiency of your cold plate to extract the heat.
Mhm.
This thermal resistance is somehow, obviously it's related to the structure, the geometry, the process that you're using to extract the heat, and so on and so forth. The fundamental issue is, and we did some analysis based on the model that we have for the next 4 generations, is this thermal resistance has to be lower and lower and lower and lower, the higher is the power of the chip. We strongly believe that at certain point, which is probably going to happen when the chip will hit 2.5 kilowatts of power, you
Mhm.
will have to have a thermal resistance so low that either you don't have the manufacturing process to do that, or you're going to force the data centers to have water in the data center that is at 10 degrees Celsius or 8 degrees Celsius. That opens another Pandora's box of problems. You
Eh,
follow me?
Yeah, I do. And what I just I have your diagram in mind here. I think 2.5 kilowatt is on the horizon of what 2027.
Yeah.
Somewhere around. So we're 3 years. No, sorry, two maybe 3 years away from that bottleneck moment. That problem.
We continue to say, "Oh my God, we have a new cold plate that can address the issue," but it's a very narrow view of the
Hmm.
future.
Hmm.
While Gemateg has been trying to develop a solution that is actually modular and address the problem going forward.
Yeah.
That's why I'm saying that our goal was not necessarily just to address the overheating of the chip. That's the starting point.
Right. But not just trying, but you've been successful at doing it. I wanted to on that note, and maybe that's where we will end here, is I wanted you to talk a little bit about the results you're getting. You were mentioning earlier 40% energy reduction, and I know you have some research, you've done some testing. So I wanted us to go through this and maybe talk about some examples of the successes you've seen at your clients.
So we work at two levels. The level number one was to perform testing at some of our customer site. And
Hmm.
what we found out is replacement of conventional cooling to our solution provide couple of important saving. Either you have a major saving in terms of energy. We were computing that you can get up to 2.3 gigawatt hour of per year of energy saving for every megawatts of computing capacity. Imagine that usually a data center, especially for this type of application, is in the 100 megawatt range,
Hmm.
or you can consume the same energy as any other solution that you have right now, but then you are increasing the computing power or 4.14 or almost zero point 0.5 petaflops. So you can do 5 billions of operation per second more every megawatt of installed capacity if you're using our solution. But that's the starting point. And it was an easy battle because we were talking about chip that were not as powerful as the ones that you've seen before. So
Hmm.
we took those data and we worked together with chip manufacturer and also with data centers, and we work at developing a model for the future,
Hmm.
trying to understand what is happening. It's a sophisticated model that fits into data from our testing, but also data from how much does it cost the installation. So it's a more holistic approach.
Okay.
Remember, Gemateg is not focused on the cold plate or on top of it.
Much more.
Gemateg it believes that the solution is an integration of inside and inside. It's an ecosystem.
Okay.
So when you go there, we did a model,
Yeah.
and I'm gonna show you something.
Mhm.
So no matter what type of solution you're using, this is the data centers, a conventional data centers where you have externally dry cooler and chiller, then you have a distribution unit that push the water everywhere. And then with our system, you basically don't need the chiller because you are relying on data to do the job smartly. And so the computation, when you're starting to go there, simply, and we did it considering generation of family of chip. And this is a very conservative estimation based on the fact that we only we only operating 100% of the time, all the time. So doesn't include all the plus that you have from operating the data centers with the ecosystem of smart control. So you can see here that you have savings that are in terms of gain, in terms of efficiency, they are in the 50, almost 50% increase just using our system compared to cold plates.
Okay. Okay.
So, and again, what I'm trying to do is not simply say, okay, we solved the problem today. We're trying to see that we are a viable solution for the next 3 or 4 years. So people can start thinking about computation and using and putting AI to work on the most sophisticated problems and not thinking about infrastructure.
This is data that you've gathered at your client's sites, right? That's right there.
So this is the slides that I showed you comes from multiple sources. Number one is data that we got for the future of the chip from work that we're having with our partners in
Mhm.
the chip world, then are coming from data at the infrastructure level with partners that are in the data centers, including those that already install our system, and they are feeding us. They are eager to send us data because they see the problem and they are suffering already. And then on top of this, we model it with the internal data that we have collected through the infrastructure that I told you. So there's almost a year of data that we have been collected working in the data centers, and they're consistent. And we have not published anything yet because we were we wanted to be sure of everything, because we don't like to make sensational statement unless we're sure what we're talking about. Those are
Mhm.
data that we can protect and defend.
Yeah. Okay. I know we all appreciate that. If we have maybe couple more minutes, are you able to give us some examples like of real cases examples of where this has been implemented, used, and what were the initial expectations going in from the places you implemented this?
I'm not going to talk about customers specifically, but we have two major installations. One is in the United States and one is in Europe,
Mhm.
where we, by the way, have our facilities.
Okay.
And it took us 2 years to convince our customers, because we needed to explain the shift from conventional cooling to active thermal management.
Mhm.
So we did a lot of testing inside of a data centers that we have a few miles away from our facility in Italy. We showcased the solution based on the customer feedback. And then once they were ready, we installed the solution to their premises. And the application are extreme, HPC, AI related. So we're not talking about simple, I know, cloud type of computing that is at our reach. So
But
we had
it could apply to that too. It could apply.
of- yeah, but again, we are focusing specifically on where the pain is more severe. And so what has happened is the installation was also a fantastic experience, because we learn a lot
Mhm.
having our team working very closely with the data center, because the operators were extremely open in sharing their pain point and their
Mhm.
concern. And in certain cases, there were also situations where we learned that our system is more resilient than we were anticipating. There were some mistakes that were taken during installation
Mhm.
somewhere else that caused our system to basically take a lot of heat, and we were able to protect the chip and
Mhm.
put the system operating safely without any type of repercussion, and also testing
Mhm.
the predictive maintenance. Actually, the more than predictive is the reactive maintenance,
Mhm.
thanks to this facility. So from that standpoint, the test on the field with the production units has passed has surpassed any expectation that we had.
Mm. Okay. Okay. Wonderful. Fantastic. It's fascinating. And I still say this after working with you for now a while and being quite knowledgeable about the company. I'm learning every time. So I want to thank you for that. Walking me through this one more time. Maurizio, I had genuinely candid questions for you, and this is a lot clearer now. Um, for the sake of this recording, for people who watch this video here, if they want to know more about that breakthrough innovation, where should they go? What should they do?
Okay, so first of all, we are now at the stage and mature enough to start making our data available to the market. So there's
Okay.
going to be more coming. There's going to be a video. There's going to be publication that we're planning to address this at various level: marketing level, technical, some semi-technical level, super technical level.
Uh-huh.
So that will and of course we are always reachable. We have an extremely knowledgeable team of engineering in Italy that has also the ability to somehow design solutions specifically to customer needs, because clearly we have an advantage with the active thermal management. And so no problem in reaching us out
Mhm.
through the website and through the conventional channel.
Okay, I look forward to seeing that information, that data coming out. Okay, that's great.